So here we have a subset of the 10 gigahertz narrowband equipment, comprising the 378 megahertz driver unit feeding a 378 megahertz power amplifier. This is generating about 4 watts or 5 watts of RF. That's feeding directly into a snap diode mixer or multiplier, which produces band of frequencies. So 27 times multiplication of this frequency is 10.224 gigahertz, and this cavity filter here, bandpass filter, feeds through a variable attenuator, absorption wave meter, a diode detector, and a dummy load. And the diode detector is feeding a scope which is on DC coupled, about 5 millivolts per division or something like that. At the moment it's switched off. I'm just going to apply power. It takes 12 volts. I just switch it on. It's drawing about a half an amp, and you can see when I switch it on, the scope trace from the detector diode jumps. There's about 35 millivolts of DC being generated by the detector diode. So in theory, if I use the attenuator, that should gradually turn the RF down, which it's doing nicely. So that's minimum attenuation. And then when I start turning this knob here, when I turn the absorption wave meter micrometer, that puts a plunger into the cavity and changes the frequency. So as the cavity reduces in size, the resonant frequency increases. So at the moment it's outside the pass band. I'll just of the filter. I'll just start screwing the micrometer in, and we should see a dip in the diode current when it gets resonant. There we go. That's me just adjusting the micrometer here. Let's see if I can get them both in the same shot. Maybe not quite. Anyway. So I'll make some dips around there. And on the micrometer scale, that's reading it's about 15, 16, about 18, no, 300, so that's 282 thereabouts. Wow, 282 on that calibration that was done 40 years ago is 10.2 gigahertz, and should be 10.224 gigahertz, which is pretty close. It's 24 megahertz out. Who knows? For a piece of wideband homebrew equipment, that isn't too bad, and 10 gigahertz band, which is half a gig wide. So there we go. I think the absorption wave meter is actually working pretty well. It's working nicely. Look at that. It's quite a high Q. A little bit of backlash in the micrometer, but it's not bad. I did try the this Varactor ×3 multiplier between the amplifier and the snap diode, and that didn't work. So something either not working correctly in this Varactor multiplier, or the tuned circuits on the input and the output aren't good for the actual frequency, which is 378 megahertz, and this is designed for 432 megahertz emitter band input to give 1296 megahertz output. So it may need some tuning of the. I tried adjusting the input tuning, the output tuning, but it didn't work. But I did find that I could get the second harmonic out of here. I could measure that on the spectrum analyzer. Okay, so it's multiplying. It's just not efficient enough to help in this particular circuit. It's better to just take the power amplifier, feed the snap diode directly, and have this multiply 27 times. So it's quite remarkable that it can produce so much diode current. So in a receive setup, that would be quite sensitive. I mean, this is producing 35 millivolts of diode current. So there's quite a bit of RF there. Anyway, there we go. I just thought I'd check that the absorption wave meter was actually functioning reasonably correctly, as one of my friends asked if it was, and I think I proved that it actually is, because this is a crystal controlled setup here, so we know this frequency is pretty good, and pretty stable on the spectrum analyzer as well. So it's certainly good enough to measure the wideband frequency of the microwave test setup I bought for the Spark Museum.